Hi there, this is Chris Collison, and we are back doing quantum mechanics once again. And we're moving forward into a smaller set of lectures. At the moment, this is going to be lecture 20, and we're following along with Donald Macquarie's quantum mechanics textbook. And what are we going to do in this particular session? We're going to, first of all, really think about the energies, the eigenvalues that come out of solving the Schrodinger equation for the rigid rotor. And we're going to think first about their dependence on this quantum number J, which comes from solving the theta equation. So as per usual, we're just jumping straight into the solution, and we're going to say, okay, we'll worry about how we got there a little later on. So without further ado, we'll go straight to some pre-written slides today, and I'm going to kind of talk you through these notes in a little bit more detail than what's written in front of you. So, where did we leave off last time? Well, we left off with a thought about solving this theta equation. Here is the theta equation that we were trying to solve, so we're going to work our way towards that. But as is common with this textbook, we're actually going to jump straight to the results and look at the solution. There's a couple of things to remember along the way. I introduced this beta term earlier in the expression. We see it right up in here. Okay, and it's important at this point to recognize that beta is definitely different. So beta is certainly not equal to B. We're going to come to a B shortly. I'm going to also just jump in by saying, well, look, here are the energy levels. This is a solution to this particular part of this particular theta equation. So, where does this come from? Well, it actually comes from the following solution. Actually, it turns out that beta is equal to J multiplied by J plus 1, and J ends up being a quantum number here. J is going to take values from 0, 1 to 2, and it's actually this solution that leads us to this expression up here. And so at this point in the textbook, we're asked to accept that this solution, this beta solution in here, beta being equal to J times J plus 1, we're being asked to accept that this naturally falls out of the mathematics. And it's actually, as I mentioned before, it's this result in here that drives my earlier expression in here in the box. So you might say, well, okay, how is this solved? So it's solved by a power series method. That's the chosen method, or the described method in the textbook. It's used to solve the equation that up here. It's used to solve this particular equation, and it yields the values beta equals J times J plus 1. So I'm going round in circles there, but that's the description. It's again beyond the scope of the textbook at this point, so we're just looking at the solutions. What is B? So if we come back to the expression in the box in here, we end up recognizing that we have a term B multiplied by J times J plus 1, and this B term ends up being equivalent now to H bar squared over 2I. So I've written this down at the bottom of the slide sort of more formally. So this is my reason for saying earlier on, beta is not the same as B. So it's very, very confusing in here. We've got this beta term that's in our theta equation, but we also have a B. B is called the rotational constant of the molecule. So what we're doing so far in this particular lecture is I'm providing you some factoids, and we're going to start thinking about where they come from as we work our way through this particular chapter. While we're talking about factoids, I'm going to also bring something to your attention. We've seen this in the guided inquiry learning workshops. Each level of energy, so each energy level has a degeneracy of G sub J. So G means the degeneracy, and it's equal to 2J plus 1. That means that if, for example, the quantum number for rotations J is equal to 2, then it turns out that there are going to be 2 times 2, which is 4, plus 1, which is 5. There'd be 5 states that shared the same energy. Okay, so we might say, let me just remind you again here, if J equals 2, then the degeneracy of that state, G sub J, would be equal to 5 according to this particular expression. Why does that happen? Well, we're going to go on to find out why that happens, but it turns out that M is related to this J quantum number, and M is going to take values from minus J all the way through 0 through plus J. And so we're going to find that degeneracy pops up a lot in these rotational for this rigid rotor. Okay, I'm only now looking at the title for the second section in chapter 2, and that is Rigid Rotator is a model for a rotating diatomic molecule. So what we end up now starting to think about a little bit in this particular section, which is section 6.2, is again a little bit about the spectroscopy. This is microwave spectroscopy for the rotations. So these transitions tend to take place in the microwave region. We can often see them in FTIR, in infrared spectroscopy, and you'll come to that if you take a course at RIT called CHMP 445. But the key point that this particular section of the textbook launches into is this another selection rule in here. We saw selection rules in chapter 5, but delta J equals plus or minus 1. That's the selection rule for rotations. We're also told that the molecule must possess a permanent dipole moment. So, for example, if we have a hydrogen chloride molecule, so let's suppose we have the hydrogen at the bottom and the chlorine at the top, we would have a dipole moment that, again, we put the plus at the bottom in here. That dipole moment points vertically towards the north. So what happens now is if we think about how that molecule might rotate, so here's our rotating molecule, so the dipole moment is permanent, and then we continue to rotate, and then we continue to rotate further, and then we continue to rotate further, and so on and so forth. So what we find is eventually we get all the way back to the beginning in here. And what's actually happened is, if we think about the dipole moment in this kind of north-south direction, what we can kind of trace out in here is what looks like a sine wave. It's supposed to look like a sine wave, and so when we have our sine wave like this, this is effectively a rotation of the permanent dipole moment that starts to mirror, or starts to look more or less identical to the sine wave that we observe with electromagnetic radiation, right? So electromagnetic radiation comes along, it's a sine wave, and how it can interact with matter is by interacting with the dipole moment. So we need a permanent dipole moment in our molecule so that once it rotates, it can couple to that oscillating electromagnetic field. So this is one suggestion, or one reason that's not explained at this point in the textbook, but basically I'm trying to demonstrate, as I've mentioned before, with vibrations, that the molecules must possess a changing dipole moment in order for them to interact with light. In this case, for rotations, you must have a permanent dipole moment. So that's that little section of the textbook explained. The next part of the book, we end up thinking about, again, we've come across these selection rules, right? So delta J is equal to plus or minus 1. So in this particular case, we're going to start thinking about how a transition occurs in these molecules. And so at once we can say, well, let's suppose we're starting from J equals 0, and we've got a plus 1 change in J. So that means we can go up from 0 in here all the way up to J equals 1. We could also start from J is equal to 1 and go up to J is equal to 2. J equals 2 goes to J equals 3. J equals 3 goes to J equals 4. And what I'm going to show you in a second is that every time we increase that number J, we find that there's some equal spacing in the energy. So for every time we go up, every time we increase the starting rotational energy level, we start to increase, if we go from 2 to 3, right, we've got a 3 times energy gap compared to the initial energy gap that we started with in here. So basically, we're going to ask ourselves how this happens, and it can be very easily explained in the mathematics. But the point here is, if I'm looking on, let's say I'm looking at a spectrum, I'm going to see equally spaced transitions to B squiggle. So these are in wave numbers. This B wave number term, we'll look at that in the next slide. But I'm going to see equally spaced lines that represent rotations from J equals 0 to J equals 1, J equals 1 to J equals 2, J equals 2 to J equals 3. By the way, we're also later going to see how these these values, actually these intensities, start to increase, because what happens is we've actually got an increase in degeneracy. So there's a lot that we can learn from rotational energy levels when it comes to spectroscopy. And we're starting to see at this point a kind of relationship between quantum mechanics and spectroscopy. And that's quite deliberate that I bring these things in. Many of you will go on to do a lot of spectroscopy in your careers, and the origins are in quantum mechanics. So let's look at some of the mathematics that are associated with this, with these spectra and these energy transitions. Let's take a look. So again, another pre-prepared slide, and this looks quite daunting from the time for the time being. But let's imagine we're in this state J, first of all, and we're going to make a transition to a state J plus 1. So we're going to absorb energy and move up to the state J plus 1. What we want to know is the difference in energy between those two states. So we'll start with the higher energy state. Let's start with energy for the J plus 1th state. And we saw this before. Remember, we have this energy expression in here, and we're just bringing that forward. Okay, so that's the equation that we're pulling forward into this slide. So really, this J plus 1, what we've got, this is really the J in here. Okay, so here's like our J, and here's this is also like our J, but remember, inside that second bracket we've got the plus 1 term. In fact, when J is simply just J in here, right, we get the equation as we saw in the previous slide. So we're taking these two terms, and we're subtracting one from the other. So I'm subtracting one from the other in here, and that's this value is being subtracted from this value. And so what I've done underneath in here is I've just expanded these brackets, and what you'll find is that when I expand the brackets for the term on the left, it's J squared plus 3J plus 2. When I expand the brackets on the right, it's J squared plus J. Of course, now I'm subtracting these two from each other, that's the minus sign in here. When I do that, I end up with a value of h bar squared in here over 2i multiplied by, in brackets, 2j plus 2. In this next piece in here, what I've done is I've just brought the 2 out, and I've cancelled, in fact, these 2's with the 2 down here. Okay, and that's how I've ended up getting this expression. Remember Planck's description of quantized energy, E is equal to h nu. So I've written this down as h multiplied by this observed frequency. And then, you know, I'm fiddling around with some more equations as I move forward. So in this particular case, I've just converted the h bar into, remember, h bar is equal to h over 2 pi. So I've got h bar squared has become h squared over 4 pi squared. So that's what's happening in here. And as I go forward in this direction, what happens is I've actually cancelled one of the h's. So I've got another expression for my observed frequency in here. So that observed frequency is going to increase as I change the rotational quantum number. What else have I got in here? So remember that B, this rotational constant, is equal to h bar squared over 2i. And remember, I also had the 2's that could be factored out of this expression. And so that ends up actually giving me another way of describing delta E in here, which was equal to 2b times j plus 1. And then what else am I doing down here? So 2b j plus 1, it is delta E in here. But also, since when we think about it, this energy over Planck's constant times the speed of light in the denominator there, that's equal to 1 over the wavelength. And 1 over the wavelength, at least when we write it in units of centimeters to the -1, those are wave numbers, right? So we have this approach where we saw this with vibrations. We can certainly do this for rotations as well. In spectroscopy, we often use wave numbers. And so there's another expression in here for this rotational constant, but now in terms of wave numbers. And so I've also shown over on the border in here how we can go from a value of B, the rotational constant, simply being equal to h bar squared over 2i, and effectively using the equations that I've shown on the way here, we take it down into units of, or at least wave numbers. So the last piece in here is to recognize that the frequency of observation now in wave numbers is equal to 2 times b squiggle multiplied by the wave, multiplied by the quantum number for rotation plus 1. And so lastly, we can then kind of go back and say, oh yeah, there's 2 beta term in here, and we multiply that by the number of the j that we go to. So let's have a look. So if j, for example, is equal to 0, if our starting point is j equals 0, then we would expect, well, j is equal to 0 plus 1 is 1. We would expect a transition energy in wave numbers of 2b squiggle, and indeed that's what we saw in the previous slide with the transitions there. 2b squiggle, 4b squiggle, 6b squiggle, and 8b squiggle. So you'll see those in that slide. So thanks for listening to this small section where we start to talk about spectroscopy a little bit. We kind of provide some of those solutions, and so next up we'll start to think about how, in fact, rotational transitions actually accompany vibrational transitions. We'll start to dive a little bit more into spectroscopy before we go back to the mathematics associated with solving that theta equation and the Schrodinger equation. So thanks for staying with me today.